So last time we discussed the Zeeman effect again, but this time we include the effect of spin angular momentum. The whole problem becomes a little bit more complicated. We have three terms with the orbital angular momentum interacting with the external field, spin angular momentum interacting with the external field, and then we also have the spin orbit interaction term. Then we discussed the strong field Zeeman effect, in which the external field is stronger than the internal field. In that case, we don't need to switch the basis to the total angular momentum description, because the more important term has to do with the LZ and SZ. The spin orbit interaction term can be taken as a perturbation, and we can do the first order perturbation result. Today, we will first finish up the other part of the discussion, namely the weak field Zeeman effect. And then we will do a discussion on the hyperfine structure, which is a very small shift in the hydrogen atom energy. And then we will move on to a new part of this atomic physics module, namely we will discuss atoms beyond the hydrogen atom. That is to say, we will start the discussion on multi-electron atoms. The first thing I would like to convince you is that multi-electron atoms are very difficult quantum mechanical problems. Not that we don't know the equations. We know the equations, only that we have to find some very clever way in order to simplify the problem and get some physical sense out of that. So our plan today is like this. So let me share the class notes. This is the last 2 pages of the strong field Zeeman effect. We can do the Zeeman term exactly for strong field, and then do the spin orbit interaction term in a perturbative, first order perturbative way. The result is summarized in this expression. We have the 0th order hydrogen energy, and then this is the strong field Zeeman, and then this is the perturbation result for spin orbit. There are 2 combinations of the MLMS quantum numbers that we need to get prepared. So for example, for p states, we work them out. There are 6 p states. And then we also analyze what are the effects of this Zeeman term and the spin orbit term. The Zeeman term split partially the 6 degenerate p states into 5 different levels, but one of them remained degenerate. And then if we take into account of the perturbation due to the spin orbit interaction term, it will just shift these 5 levels slightly. 2 of them will not have any shift at all, because the combination here happens to be 0. And if we work out the possible transitions due to this splitting, say a p state into 5, and then a s state into 2, and then some selection rules, it will happen that we will still see the normal Zeeman effect, namely one spectral line without the field effects, internal or external, will give us 3 lines. So we still have a puzzle. Previously, we mentioned that there is something called the enormous Zeeman effect. And what happened is that one spectral line will split into even number of lines. And that is related to the case that we will discuss now. It is the weak external magnetic field Zeeman effect, or in short, weak field Zeeman effect. The whole Hamiltonian will have a spin orbit interaction term and some Zeeman term. By weak field Zeeman effect, we simply mean that the internal field or the spin orbit interaction part is more important than the external field, the Zeeman term. Thereby, we must choose to do the spin orbit interaction term first. We do it more seriously, then the Zeeman term do it in an approximated way. So the first problem we have to handle is the atom Hamiltonian plus spin orbit interaction. Fortunately, we already did this part in the fine structure discussion. So if you forgot what we did, go back and see the section on fine structure. All in all, when we see S dot L is important, we go into the new description using J, the total angular momentum, and its Z component with the quantum number mj. So we are already finished with this important part of the problem. And then what happens is that there will be splitting of the, say, P states into two levels according to the J. For L equals 1, this can be J equals 3/2, 1.5, and then this is J equals half. They will take on different energies, and there are hidden degeneracy here according to mj. So the Zeeman, the spin orbit term will remove the P degeneracy again partially. With this as our basis, then we hope to treat the Zeeman term in a perturbative way, first order perturbation. Okay, so that is the idea. So now we are ready to handle the Zeeman term. Last time, we emphasized that the Zeeman term has one unpleasant feature. Because of the difference in the G factor, the spin G factor is 2, the orbital angular momentum, in the orbital magnetic dipole moment, the G factor is 1. Due to this difference in the G factors, we have L plus 2s dot into the external field to give us the Zeeman part of the Hamiltonian. The bad thing is that this is not J. Instead, it is J plus S, right? L plus S is 1J, and then there's an extra S. So this thing is not J, but is J plus S. Now, we want to do perturbation. The first thing is first order perturbation, right? So first order perturbation, but in our basis, using JMJ to describe the Zeeman spin orbit splitting, we encounter one problem. The perturbative Zeeman term is not just related to J. If it were, we will be very happy, right? If this is a J, it will pick up this J, and then we know what happened, right? It will give us a JZ, MJ, and then it will be MJ, H bar, everything will be done in one step. However, in this case, we don't have a J here, but we have J plus S, okay? Thereby, we need one more approximation than just the first order perturbation to handle this term. But we think it's okay, because after all, we have done the more important part. The spin orbit part is already done. This part is meant to be weak. So although it is not proportional to J, we hope that it will become proportional to J, and then we will see how we can do the approximation. Now, a very rough approximation will be, let's ignore this S and then it is proportional to J. Now, that is already, I would say, not too bad, right? I have L plus S plus S. Out of 3 terms, I handle 2. Not bad. Then, can we do slightly better than that in order to keep this thing, this ugly thing, to be parallel to J? Okay, so the idea comes. How about we project this S along J to take that particular part? Then we are not completely ignoring the extra S. We keep some of the effect of this extra S. So that is the idea. Okay? So the idea is that we hope to maintain the dipole moment to be parallel to J. And hopefully we can do it by representing the prefactor, another G factor here by some number. Can we do that? How can we do that approximately? So that is the technique involved or approximation involved here. Let's say we can do that. Okay, we still not know how to do it. Let's say indeed we can do this approximation. Then life will be easy. The external field set a Z direction that will pick up JZ. In the dot product, JZ will look for this quantum number, and immediately in one step, it will give us MJH bar as the eigenvalue. This combination is the Bohr magneton. So again, we have a very simple answer. If, big if here, we can assume the total magnetic dipole moment to be parallel to J, although it is not in the formal expression. Okay, so at least we have found something that we want to do. We hope that we can do it, okay, as an approximation. So let me summarize. The idea now is, if we can make this approximation, then the answer will be very simple. This is the first order shift due to the Zeeman term. And then we want to do this approximation. We want to find out what this number will be. Okay, this is a big thing. It will be called the lambda G factor. After Lambda, who did that in, I think, 1930 or so, Lambda was another student of Somerville, I should say, like Heisenberg. So we have some goal here. So let's see how we can get at this approximation. So as I already hinted at, we have L plus S plus S. L plus S is a J. That is good. We want it to be parallel to J. We have something already there. But the extra bit is an S. We don't like this because J plus S will be another direction, not J. So the idea is that, how about this? We only take into account of the effect of S, the part that is projected into the direction of J. Then we will have something that is slightly longer than J, so account for a bit of the S, but still parallel to J. So that is the idea. Well, once you have this idea, it's easy to carry it out. So we want a projection. Then we play with vector, right? S dot into a unit vector along J, that is the component along J, the component of S along J. But we want it to be a vector turn it into a vector along J. So the unit vector along J. Okay, so this is the key steps to execute our idea. Project S onto J and only take that component. Okay, so do you understand this particular combination? Once you get through it, everything is easy. Is that okay, guys? Okay, so now we will take this and then add to J, then we will have a vector that is parallel to J, and we are done. Now the goal is to look for this extra contribution, and how will it change this prefactor, this number G, the lambda G factor. Okay, so let's work it out. So this thing is nothing but S dot J here. This is the direction J, that's good, divided by the magnitude square, J square. Okay, now J dot S is easy to handle. It is nothing but J square minus L square plus S square. Okay, so we have an expression for this little part due to S along J. Okay, then what we are saying is that we will make this approximation. J plus S formally is not parallel to J. We ignore the part that is perpendicular component to J, take it, neglect that, and only take the part that is along J. At least we take into account something of the extra term S. And that is this part. Okay, so we are basically done, succeeded in our ambition. Okay, so now we replace L dot S by this chunk and go quantum. We replace it by all the things by the operator. Then every one of this can find its target. J square will look for J, quantum number. L square look for L, L plus 1. S square look for the half. Okay, SS plus 1. And also this J square will look for J. Okay, so suddenly in one step, this thing becomes a number. Okay, now this is the original part, the J here. Okay, and then this extra bit is related to our further approximation, taking S along J. All right, now we succeeded in doing what we want to do, but we have to look at this particular combination of quantum numbers that will give us a new G factor. That is just a number of order 1. So we call this combination the lambda G factor. After the first scientists who worked this out, that is before quantum mechanics. I should mention that. Lambda was simply working on spectrum, atomic spectrum, and try to understand the splitting. So this whole combination will be called this lambda G factor. Okay. Now, recall last time we discussed something called the term symbol, or the chemists also call it term value, I think. The term symbol. It is a very compact form, right? We have the L in the middle, the J in the lower corner, and 2S plus 1 in the upper corner. Okay, just remind you of that. Do you see? If you see a term symbol, you can calculate the lambda G factor because the information L, J, S, the 3 numbers here in equation 51 are embedded in the term symbol. Okay, so things are related. So once you have the term, actually you can also calculate the lambda G factor out. So now what happened is the following. Previously, when we first discussed Zeeman effect, only the orbital angular momentum effect, we saw this splitting due to the quantum number ML. And there is a G factor is 1 for orbital angular momentum. What we have done here is very similar. We copy through all these things, but then with this spin orbit interaction come first, we have to switch to J, and then this Zeeman effect with spin included will simply give us a modified G factor. The combination that we work out, the lambda G factor, otherwise the expression looks almost the same. So the Zeeman effect will split the degeneracy behind J. Now it depends on MJ. So for example, P state, L is 1, spin is half, J can be 3/2, 1.5, all right? Now, MJ in that case can take on 4 values, 1.5, 0.5, minus 0.5, minus 1.5. So with the external field, this J value, 3/2, will give us 4 levels, okay? Similarly, for J equals half, it will give us 2 levels. With this splitting, say the 1s give us J equals half, 2p give us 4. Now, even numbers now, when we apply the selection rule, it happens that we will get even number of spectral lines. 1 line, even number, 2 lines, okay? Or 4 lines, okay? So now we can explain enormous Zeeman effect. So let me give us some example. So here is a P state. You can take it as 2p if you like, but NP, 3p also works this way. Now, without any terms added to the hydrogen atom, the P states are degenerate. The spin orbit is more important in the weak field case, so that will split according to J first. 4 states here behind MJ, 2 states behind MJ. Okay, no more, no less, 6 states. Now you apply a weak external magnetic field. Zeeman splitting says it will split according to MJ. Okay, now the splitting here between levels will be G factor mu BB, the Bohr magneton times the external field. All right, so again, it's even, but with a G factor, it may be something like 1 point something, 2 point something, things like that, okay? So what is the consequence? Let's look at the first Lyman series line that goes from 2p to 1s. If our apparatus is not so sensitive, or in theoretical term, we ignore everything, only the atomic part of the Hamiltonian, we will see 1 line. And we know the difference, and this is 1 line. Now, with the spin orbit interaction, this is the fine structure. No external field yet. The P state will split into 4 in one group, 2 in another group according to the J. These are the term symbols we introduced. And then we will have 2 nearby lines. around the original one line. All right, so this is the fine structure. In sodium, that will be the yellowish sodium doublet. Now we will turn on the external magnetic field. Now, here I just want to remind you that term symbols introduced last time, all this information can go into calculating the lambda G factor. I do the example here for this particular P lines split into J equals 3/2. The G factor is 3/4. For this particular one, the G factor is 2/3. So they are different according to the J values. Now, turn on the external field. It's weak. Actually, the effect is much smaller than I drew it here. I exaggerate the effect so that you can see it more clearly. What would be the effect? Before you turn on the external field, we have this two fine structure splitting. The dashed line here, this and that, okay? Now, these two dashed lines are the two here. All right? Now, let's look at the energy levels first. The J equals 3/2 in the presence of an external magnetic field will split according to the MJ value. Okay? The energy difference between neighboring lines is related to the lambda G factor for this particular group. We calculated it out. It is 4/3. Similarly, for J equals 1/2, external magnetic field will split it according to the MJ. The splitting depends on the lambda G factor for this group. This is different. This is 2/3. Okay, 0.67. So therefore, you notice that the difference here is different from the difference here in this picture. Again, largely exaggerated. Blow it up for you to see, okay? So it is not to scale. Similarly, for the ground state, 1s, in the J label, it is J equals 1/2. It's L equals 0 plus spin 1/2. 0 plus 1/2 is 1/2. Okay? Now in the external field, it's split into two levels according to the MJ value. You should work out the lambda G factor again because L is 0 here. Okay, so it's a different number. Now, you see, we have 6 up there, 4 in a group, 2 in a group, and the 1s becomes 2. Then we will exercise some selection rule for allowed transitions. I just stated here. I'm not explaining it yet. We need another skills, namely time-dependent perturbation theory. We will discuss it later in order to understand why we have selection rules. At this moment, I just make use of this allowed delta MJ must be either 0 or plus minus 1. So when we exercise this selection rule, you can draw it out. If I start here, MJ is 1/2. Where can I go? All right. Now, I can go to minus 1/2 because delta MJ will be plus 1. Minus 1, right? Final is minus 1/2. Minus initial is another minus 1/2 is minus 1. Okay? Or I can start here and go to plus 1/2 is okay. It is delta M equals 0. So Starting here, I have two allowed transitions. Okay, understand me? So I work out all the possible ones starting from every state in this upper 6 states. The arrow shows the 10 possible transitions. Then you can work out what are the energy difference. That will be the spectral lines. Now you see, very interestingly, instead of the fine structure, one line here, it gives 6 very closely spaced lines. And for this one, there will be 4 very closely spaced lines. So let me summarize. Last term, as a baby level model, you learned the first line in the Lyman series. It is just one line, minus 13.6 divided by 4. Up there, minus 13.6 down there. One transition, one line, okay? Now, after this chapter and some perturbation technique, we understand that in highly accurate spectroscopy, namely, you use laser to plot, you have sensitive spectrometer, good detectors. This line happened to be split into 10 lines when you apply a weak field to it. Okay? So we have done something rather profound, I would say. So this is the situation. I use sodium as the example. Without the magnetic field, we have this doublet, yellowish doublet. But now, turn on the magnetic field, not so strong one. This goes into this goes into that. Okay? And this is the case. You can observe this in sodium more clearly than hydrogen. So finally, I would like to make some final remark for this section. I think we have made good progress. If you understand everything, you equip yourself with rather strong physics background in atomic physics. So we studied the Zeeman effect. And then once upon a time, Zeeman effect, Zeeman got the 1902 Nobel Prize, well before any quantum mechanics was developed. So we saw that Zeeman effect, an experimental approach. Take a gas of atom, applied magnetic field, look for the spectrum, actually had led to many developments and important developments in the ideas, in the concept, in the techniques, in quantum mechanics. In order to understand this Zeeman effect, we need to develop many quantum mechanical ideas. We need to know how to handle dipole moment interaction with fields. We need to know the spin angular momentum and its associated magnetic dipole moment. We need to know how to add them, okay, into total angular momentum. And then that also leads us to the fine structure, even in the absence of the field. Only after understanding that, we can go back to have a more complete understanding of the Zeeman effect. So I think it's a good scientific story about the development of science and physics in particular. Okay? The last one is a remark I already made. Historically, Lander actually did this whole thing before quantum mechanics was established and before the spin idea was invented. He was just trying to understand spectrum. So what you did last term, was that you only know one line. And then if you read only quantum physics or or modern physics book, you only get a descriptive exposure to this Zeeman effect, spin-orbit interaction. You never see exact equations. But in our course, we only rely a little bit of quantum mechanical skills, the Schrödinger equation, angular momentum in quantum mechanics, we derive the general results, and then we do a lot of finding out the Hamiltonian by think classically first and then go quantum with operator. And more importantly, we are equipped with a few not so fancy approximation methods. We do a lot of first order perturbation, not even the second order, right? But then with this, we can do quantitative treatment to this additional terms to the hydrogen atom problem, okay? So what we did include spin-orbit interaction fine structure, relativistic correction that goes into the fine structure, and then the Zeeman term, including the effect of orbital and spin angular momentum. All right, so it is rather profound. Well, I mean, you gain a lot by knowing a little, I would say. So that ends this part. The very last part of hydrogen, let me see. There is a question. Why S is labeled as, oh, okay. The question was, why do we use 2s plus 1 in the term symbol instead of just S? A simple answer, I think we have to go to the experimentalist point of view. 2s plus 1 give us how many lines? You see? For example, if S is half, you will get a doublet. Understand, Mr. Tai? Okay, so that will be a more straightforward way to express how many lines. Okay, so you have to accept physics is an experimental science. Again, I'm a theorist in training, but I would like CUHK students to really appreciate physics is development relied on experiments. Okay, then there is another one. Okay, now this is a very good question. The question is about in the middle of the process of making the approximation, I encounter something like 1 over operator square, right? Okay, so again, you are thinking highly periodically, okay? I will say that is an empirical approach. So when I do the projection, I have 1 over j square as the length square. Then when I go into quantum mechanics, the idea is simply to replace j square by j times j plus 1 when I hit the quantum number. Okay, I don't have a better explanation for that replacement than simply it is empirical. Okay, that's why I said Lambda did this in 1921, well before you have this fancy thing, operator, things like that. Okay, and then it works because it works. You know, that's physics. The Schrödinger equation, it works because it works. Okay, and I think we are also fortunate in the sense that in this weak field case, the spin orbit using J already captured the big part. Okay, so let me continue. It is a small part. Previously, I will skip this, but in recent years, again, physics has, has been ever changing. But in recent years, this part turns out to, again, become more important than before, at least as a culture, as a common sense in physics. So I would like to discuss a little bit about something called the hyperfine structure or hyperfine splitting in the hydrogen atom. That also happens in other atoms, but in hydrogen is now the most important thing to know. So let's recap what we have so far. What we have so far is that last term, you know about this. When we include spin-orbit interaction, no external field here yet, right? Okay, so when we include a spin-orbit interaction and other relativistic effect, it will split according to the J and N. Okay, and that is in agreement with the treatment using Dirac equation. And now, we also know that comparing with experimental data, there's a part that we cannot explain. It's called the lamp shift. The same J value will not give you the same level, but slightly different ones. That has to do with the vacuum effect. We need QED to do that. So that is the story so far. However, the story continues when experimental detection technique becomes more and more precise, more and more sensitive. So what we have discussed so far are related to the Baer-Coulomb interaction, the spin-orbit thing, okay, and also relativistic correction. And in the spin-orbit interaction, we know that we will encounter an S.L term when the two angular momentum or magnetic moment interact. And this page is an idea quite important in concept. When we look into the energy, allowed energies of an atom, many of us tend to think in terms of an atom behavior, an electron behavior. For example, electron go from this level to another level, okay? But if you think about quantum mechanics, the Hamiltonian is about the atom. So it will be more useful if you think about the allowed energies as the allowed energies for an atom as a whole, not only thinking about it is due to the transition of an electron from one state to another. That idea will be important, for example, in many electron atoms. In many electron atoms, we better think about the atom, say, different energy may be different color. So you can think about, oh, the atom changed it, well, just in a cartoon way, the atom changed color. From one color to another, there is a different energy, okay? So that will be a useful way to think about the physics. It is useful because many things interact. And when the particles or the properties of the particles interact, it is more difficult to think about some property of this interacting thing due to one of the constituents, one electron, okay? So now, let's go into hyperfine structure. Now, it is related to something that we have not been considering so far. It has to do with the nucleus of the hydrogen atom, which is a proton. Okay, that is simple. So we look into the nucleus effect. For the nucleus of a hydrogen is a proton. And proton, charge plus E, that part we already handled. It gives the Coulomb attraction. But we haven't considered the spin of the proton. Proton is a fermion, its spin half. Proton has charge plus E. Therefore, we expect that it has a magnetic dipole moment. Indeed, it does. It has an expression that is very similar to the electron one, only that we need to measure the proton G factor. Last week, we mentioned the muon G-2 experiment, right? That is muon's G factor. So all this particle will have its own G factor to be measured. So experimentally, the G factor of proton is found to be 5.6. And this happens to be important in medical applications. In something called magnetic imaging, resonance imaging, actually what we are probing is about the spin splitting of proton. We have a lot of proton because we have a lot of water, and water is H2O, and we have 2 H in each water molecule. And then there will be 2 proton nuclei in each water, and we are probing the splitting of this proton magnetic dipole moment in a magnetic field. Okay, so now let's get some idea. This is a tiny effect. Why so? We know that in electron, we will hit at an electron Bohr magneton. I emphasize that it is something like 10 to the minus 4 Tesla, 10 to the minus 4 eV per Tesla, already very small. However, for proton, the nuclear magneton will have the electron mass replaced by proton mass, which is something like 1850 times bigger than electron mass. Okay, 2000 times roughly. With this, it means the nuclear magneton magnitude, the number, will be 2000 times smaller than the electron Bohr magneton. By that, we will expect this order of magnitude, 10 to the minus 8 eV per Tesla. All right. So this, if we take into account of this, and if there is a splitting according to the spin plus minus half, you know, this is the order of magnitude splitting we will expect. So this is why we have this hyper fine. It's finer than fine. Okay. Nonetheless, it turns out to be a very important effect that scientists can look at in investigating the universe. Okay. So I think at this point, I would like to take a short break, and then we will continue on this part before we move on to bigger atoms.